Start, Divya.
Good afternoon, everyone, and I am Divya, volunteer of Reactive. First of all, I would like to welcome all of you to Reactive's 151 episode of Reactive Online Weekend Talk. We gathered here to inspire creativity. This weekend, we have an excited lineup of speakers, Dr. Josna KM. First of all, I would like to say few things about Reactive. Reactive is a group of people who are eager to gain new knowledge. Knowledge Square is our tagline. Sharing of knowledge increases our knowledge. And vision of Reactive is to build constructive thinking on various domains. And this weekend we have an opportunity to engage and participate in interactive session on 2D material based nonlinear optical mirror for upconversion imaging. Here we explore new things on 2D materials. Before starting our today's session, I would like to give a brief introduction about today's speaker, Dr. Josna KM. Dr. Josna KM is a PhD graduate from Department of Electrical Communication Engineering, Indian Institute of Science, Bangalore. Her areas of interest are nonlinear optical microscopy, mid-infrared imaging, super resolution microscopy, upconversion imaging, biomedical imaging, image processing and quantitative analysis, and electromagnetic modeling of optical systems. She studied nonlinear processes such as four-wave mixing, two-photon absorption, two-photon photoilluminescence, harmonic generation in the thin film, quantum dot, metasurface nanostructures. Her contribution to the field of photonics is marked in the form of 14 journal articles, 12 conferences, proceeding papers in reputed journals, conferences, and one patent application process. Actively involved in professional groups like IEEE, Optica, and SPY, and has chaired the IASC student chapter Applied Photonics Initiative during 2022-23. She started her research career as an intern at Biophotonics Laboratory, Yungbuk National University in Republic of South Korea, where she was an exchange student from Christ University during her MTech program. She was MTech rank holder and recipient of Best PG Student Award for Excellence in Academics for 2 consecutive academic years. And this is about our today's speaker. And I'm welcoming you, ma'am, for this session. And I'm welcoming all the participants of Reactive. Thank you. Over to you, ma'am.
Thank you, Divya, for the kind introduction, and thank you, Team Creative, for giving me this privilege to present one of my thesis work here in this event. So, as I mentioned, this is one of my PhD thesis work, and I'll be focusing on 2D material-based nonlinear optical mirror for upconversion imaging in this particular talk. So this is the content in which I'll be presenting today. I'll brief about the motivation behind working towards this 2D material-based nonlinear optical mirror. I'll give a small introduction on the need for converting IR information to visible signal, techniques previously implemented to convert this IR information to visible signal, and I'll brief about the nonlinear optical processes which are generally used. And I'll explain in detail some of the wide field of conversion imaging like design consideration, previous literature review on previous implementations, and finally our work on conversion. I'll give some experimental results, and finally I'll summarize with the observations. So infrared radiation is a type of electromagnetic radiation with a wavelength longer than visible and shorter than the microwave. So they span from a wavelength range of 0.75 to 14 micron. And the technique of allowing one to capture this images of the infrared spectrum is called infrared imaging. And it has got a lot of application in various regions like spectroscopy. So particularly mainly to inspect in the context of spectroscopy. It's mainly used to inspect the molecular composition in biological samples. For example, you can see in the figure here, most of the biomedical samples have their molecular resonance in the mid-IR wavelength range, which generally spans from like on the longer IR wavelength range, that is 1 to 10 micron. And people have used mid-IR radiation to excite these samples and understand the molecular compositions. And this particular wavelength range is often referred as the molecular fingerprint region. And in case of another application could be to use an industrial inspection for non-destructive imaging and heating of the sample, and in defense for surveillance and night vision and medical diagnostic, environment monitoring, and in astronomy, particularly to study like the clouds, dust clouds, etc. So the core of an infrared detection imaging system is the infrared detector, and they can be broadly classified as a photo detector or a thermal detector. So some of the existing infrared detectors are indium gallium arsenide detectors, indium antimonide, mercury cadmium telluride, and lead sulfide and lead selenide. So some of these work at under different IR wavelength range. So mercury cadmium telluride has been widely used in which covers actually a long range of infrared radiation, and they have been widely used in many imaging systems like FTIR imaging system, etc. But there are certain challenges associated with the existing infrared detectors, which include low efficiency and limited dynamic range. And most of this infrared radiation have lower energy, thereby requiring the need of narrow bandgap semiconductors. And some of them are sensitive to thermal noise. And for this, we have to use an additional cryogenic cooling system, which make the actual detection system bulky and costlier. And some of the, you can see the image of a focal plane array, which is actually bulky and making it highly costly, and some of them have export restrictions as well. So to overcome this, one method is to convert the infrared signal to visible signal. So what is the advantage of converting the IR information to visible signal? We have a wide range of like silicon based detectors which are much advanced and readily available at various price points. So it's a good idea to convert IR information to visible signal. Thereby, you can get better efficiency. It can provide a wide range of dynamic range, and also they are not much sensitive to thermal noise. And in the cost wise, it is much cheaper compared to existing IR detectors. So we need to convert the IR information to visible signal. So there are several techniques which people have already used to convert the IR information to visible signal. One such technique is using photothermal imaging. So how it works is we use an IR radiation that heats that cause a local temperature increase in the sample, and we use an additional probe that is in the visible range. So what happens is this local thermal change actually results in refractive index difference in the sample, which actually modulates the pump beam result, and this pump modulated pump beam is detected using a normal visible detector. So here again, can make use of the advantages of visible detector. So this is one representative image, in which they image adipose tissue using this particular technique at on and off resonance. And another technique is to use convert this IR information to visible using a nonlinear optical processes. So there are certain demonstration of using like some frequency generation. So I'll go in detail of this nonlinear optical in the coming slide, nonlinear optical processes like some frequency generation in the coming slide. So what we use, we have a long wavelength IR signal, which is sensitive to the sample or which need to be up converted, and we use an additional probe of shorter wavelength, which in the nonlinear media, which results in a generation of new photon at some wavelength, at some frequency that is like which is at a much shorter wavelength, resulting in detection in which visible region, and this can be easily detected using a visible camera. So this is one representative image that shows a image of a collagen using this some frequency generation process at on and off resonance. So another completely different method is to use quantum ghost imaging. So you can use entangled mid-air visible photon pair and keep using we can use a nonlinear crystal to generate this entangled mid-air photon pair and keep the sample in the mid-air signal in mid-air signal path and detect the interference from these two paths to come up with a come up with an image of the sample that is being kept in the visible path but detected using a visible camera. So this again requires a high sensitivity detector and generating an entangled photon pair itself is a bit complex, making this entire imaging system complex. And another recent demonstration shows the use of non-degenerate two-photon absorption of the detector itself. So you don't need an additional convert the information. You make use of the non-degenerate two-photon absorption of the detector using an additional probe to detect the mid-air information. So here again the phase matching requirement is not necessary, and you don't need an additional non-linear media as I already mentioned, and makes the entire system simpler. In this work, we'll be focusing mainly on up conversion using nonlinear optical processes. So let me brief what is a nonlinear optical process. So nonlinear optical process refer to a phenomena where the material behaves non-linearly with respect to the applied electric field. So this happens when we apply a high field intensity onto the sample, which have a good, strong non-linearity. So polarization varies non-linearly with respect to the applied electric field, which results in electromagnetic radiation at a smaller, at a shorter wavelength. So the process can be converted into two second order processes and third order processes. So some of the second order processes are second harmonic generation microscopy, some frequency generation microscopy, and difference frequency generation microscopy. And third order processes are sensitive to chi3 component of the material, and our processes include third harmonic generation, four-way mixing, third order some frequency generation microscopy, coherent anti-histogram and scattering microscopy, etc. So I'll go detail of the into the some frequency generation processes because we are using this particular method for up conversion in this work. So before that, I'll brief about second harmonic generation. So in second harmonic generation, what we use photons of same frequencies being absorbed in the nonlinear media, which is having a strong chi2 component and resulting in a generation of a new frequency at the twice of the new photon at the twice the frequency or half the wavelength. And in case of some frequency generation, we use two photons, but their frequency is different, and the resulting photon generated will be at the sum frequencies. So at the resulting frequency here, it's at a sum of the signal and pumping. So for this, we need a nonlinear media with a strong nonlinear process or like a nonlinear property or chi2 component. So let's go to the main topic, that is wide field up conversion imaging. So upconversion imaging, as I mentioned, is a technique in which the IR information is frequency converted to a near IR or visible image through a certain process like nonlinear optical processes, then thereby detecting using a silicon-based camera. So one advantage is better sensitivity, speed and noise performance due to the visible detectors, and they also allow wide field imaging. So the first ever demonstration of this conversion imaging was in 1968 by Midwinter, where he up converted 1.6 micron to a visible wavelength of 484 nanometer, and he used a bulk nonlinear lithium niobate nonlinear crystal. So you can see this is one of the literature. I took this image from a literature review, which showed that there was no much advancement in this field till the late 2010, or after which there was a slight increase in the interest in this domain. And this main lack of the progress could be due to the limited choice of poor quality of the nonlinear crystal that existed back then and the detectors. So in now there has been slight interest in this upconversion imaging techniques, and let's see what are this. So first, let's understand what are the design considerations for upconversion systems. So a nonlinear media with high nonlinearity is preferred. So whatever process you're trying to study, we need a material with high nonlinear nonlinearity, and the material has to be uniform. For example, you can have a large crystal or aperture in the case of crystal based up conversion, so that you can get a wide field, large area for large field of view for the up conversion systems. And most importantly, all the wavelength that is interacting with the nonlinear media should be the material should be transparent to all the wavelength of wavelength interacting with the sample. And this obviously the sample should have higher damage threshold. So the previous implementation mainly used nonlinear crystals, as I mentioned, and they have strong nonlinear optical property. Some of the examples are potassium niobate, lithium niobate, and for phase matching requirement, we normally use periodically poled lithium niobate crystals. So they are specially engineered to have a better space matching within the structure, and their efficiency are quite high, particularly for second order. There has been a lot of demonstration using second harmonic generation and other parametric processes. So the figure here shows some examples of upconversion in recent upconversion image. Here you can, they have used a USAF target sample for upconversion imaging. But there are certain limitations associated with nonlinear crystals because they're bulky. As I said, the crystal size need to be large enough to have a good phase matching and a large field of view. Okay. And the cost associated with growing this high quality crystal is high, and they have limited. So for example, you need the material to be transparent over a range of wavelength, right? So that there is certain limitations associated with that, and they are less thermal sensitive, and and they're also sensitive to the environment conditions. So these are some of the examples of previous upconversion done using nonlinear crystal. And so in very recent publication, there is a use of meta surface for upconversion imaging. So this actually overcome certain limitations of the liquid crystal. For example, they are much thinner and compact, so making this can be easily integrated to any system, making them the entire imaging system much compatible compared to a system with nonlinear crystal. So here they make use of an array of nano antennas which are especially designed to perform. So in this particular work, they have used some frequency generation itself in the nonlinear media to upconvert the 1530 nanometer to 550 nanometer. And they, as I mentioned, they use a array of gallium arsenide nano antennas, which is used for wide field upconversion. So here, the certain limitation associated with this is they provide limited efficiency because they have higher diffraction, because each of the individual uni nano antennas are actually contributing to the overall upconversion, and there could be some fabrication defects or something that can actually deteriorate the quality of the image being image being generated. And most of them are sometimes polarization sensitive, etc. And most of them depend on the incident angle of the incident beams in the overall efficiency. And the very recent paper also have used a silicon membrane metasurface, which with a better imaging performance. And they again use another nonlinear process called third harmonic generation, wherein they use 3 photons of 1512 nanometer to get an up converted photon at 504. So these are the some of the recent works on metasurface for IR upconversion. And so given these limitations, we are proposing the use of a 2D material based nonlinear optical mirror for wide field upconversion imaging. So why 2D materials? So 2D material is a new class of optoelectronic device with high quantum efficiency, and they have strong nonlinear optical processes, and they are designed such that they have a strong chemical bond in plane, but a weak van der Waals bond on the out of plane. So which make them very easy to be exfoliated or transferred. And very importantly, they have very high nonlinear response, and their atomic layer thickness is very less, like less than few microns, so which makes the entire imaging system much compact, similar to that of metasurface. And but they provide a better power conversion efficiency compared to metasurface because they are uniform and there is no much complex fabrication process required. You can easily exfoliate these onto the structure and get a very uniform region for imaging purposes. And most importantly, they can be easily integrated to any existing imaging system. So in this work, there are certain lot of existing 2D materials being studied like graphene, HPN, MOST, etc. In this work, we make use of gallium selenide. So why gallium selenide? Because it has a good optical transparency in the wavelength which we are interested in, like 0.6 to 18 micron. And they have a layer independent non-centrosymmetry. So they have like strong second order response, which can be used for upconversion. And in this particular work, we are demonstrating an upconversion of 1550 nanometer onto a near IR 622 nanometer using a pump beam of 1040 nanometer. Okay, so generally how this 2D material is being designed is like they have a silicon substrate, we transfer this 2D material onto this, and that is a general reference sample normally everyone prefer. Here we make use of, we do additional modification, we add a gold film on below this 2D material, enhancing their enhancing the efficiency of the entire system. So basically the thickness of the 2D material and the intermediate SiO2 layer has a lot of importance in the overall SFG signal generation. So we actually optimize the thickness of the gallium selenide and the SiO2 thickness by using a particular particle swarm optimization algorithm. So as I mentioned, the 2D material based nonlinear optical mirror, we have a 2D material below which we have SiO2 and below which we have the gold film. And the thickness of the gallium selenide and SiO2 is actually optimized using this PSO algorithm. So PSO algorithm, what it does is actually we have an objective function that it actually try to minimize to get the maximum optimized signal. So here the objective function defined is the inverse of the SFG signal that is being collected. So this mirror is actually designed in COMSOL multiphysics software, and the SFG signal generated at different thickness values are actually given as an input to the particle swarm optimization algorithm. And the thickness for the maximum SFG signal, that is the minimum figure of merit value, is given as the output for the space optimization algorithm. So in this case, particular design, the optimum thickness for gassy was obtained as 45 nanometer, and optimum thickness of the SiO2 was obtained as 50 nanometer. And the SFG signal with this particular optimized design is 43 times compared to the normal reference sample with SiO2 thickness of 300 nanometer. So this is the optimized design of the nonlinear optical mirror we designed. So we have the gassy flake of 45 nanometer thickness, which is exfoliated onto the SiO2 film of 50 nanometer, below which we have the gold film. And this is the result of the PSO optimization algorithm, where you can see over iterations, the figure of merit decreases, which actually gives the maximum SFG signal. And this is the corresponding thickness of the gassy and SiO2 at various iterations. So we again, so this was a simulation result. Now we validated the simulation result by actually transferring this optimum thickness gassy on the designed 2D material and on the reference sample. And these are the images obtained. And this image was obtained by scanning the sample and imaging using a photo multiplier tube. And you can see that the enhancement in the nonlinear signal is 43 times compared to the reference sample with a similar thickness on a reference sample of 275 nanometer. And we were able to see that SFG signal with different gassy thicknesses was completely correlating with the simulation data. And we also did a power dependent study. So for example, first we have to understand this nonlinear signal generated is from SFG And so for that, we have to do power dependent study. So since the process of SFG involves single photon of pump and single photon of IR, we expect to get a linear dependence in the power, and we have obtained that in the experiments. And we also did a polarization study. So polarization study was done to understand the SFG generation is actually from the gallium selenide, and the hexagonal symmetry was actually portrayed in the polarization study, which showed a six-fold symmetry in the data. So now I'll explain more about the conversion imaging system. So we have the optimized 2D material-based nonlinear optical mirror, which is fabricated with with the optimum thickness of Gaussian SiO2. So the system so what this system does is the weak IR or mid IR photon, whatever need to be up converted is given as an input, and the whatever sample that need to be up converted, like whatever image you had that need to be imprinted, is kept in the particular imaging plane, and we actually image this and you. There can be two different configuration in which you can do. One is real plane imaging. Another one is Fourier plane imaging. So in the one case, in real plane imaging implementation, what happens is the actual sample that is kept in the IR path is imaged onto the sample plane where the 2D material is being kept, and that is imaged further onto the EMCCD camera. And in case of upconversion using Fourier plane, the object plane is imaged onto the back focal plane of the object plane is imaged onto the back focal plane of the objective, which is further imaged onto the EMCCD camera. So we to image this object onto the back focal plane, we make use of 4F lenses. So 4F lenses or 4F system, which the imaging system here mentioned here is like 4F lenses. So 4F lens is nothing but like a pair of lens that actually image one imaging plane to a particular plane in the optical system. And here again, we make use of EMCCD to detect the visible signal. And yeah, I'll show some of the image. You'll be clear by then. So this was the transferred flake onto this optical image of the transferred out flake, and where you can see a very uniform region in which the flake was transferred, and thickness of the flake was measured as 45 nanometer with AFM. And this is the SFG image of the point. This is the scanned image of the flake, and this shows the converted image without any target in the path. And these are the fabricated target which was placed. So these are the different objects being placed in the path, which you can see is being imaged onto this flake, and you can see the converted image which is being detected using an EMCCD camera. So these are the demonstration of IR upconversion imaging, in which we made use of an SFG to upconvert. And so this is a detailed experimental setup of real plane imaging and Fourier plane imaging system. So I'll explain this in detail. So you can see, as I mentioned, here we are trying to upconvert a 1550 nanometer to 622 nanometer. So this OPO is the source for 1550 nanometer. We have a under fiber laser at 1040 fixed wavelength. So these two are the source for the particular nonlinear optical process, which we are planning to use for upconversion. And this is the sample, or this is a USAF target which we place in the path. So the sample is placed in the IR path, which need to be upconverted. And this, as I mentioned, is imaged onto the sample plane. So here is the 2D nonlinear optical mirror. Here is where we place the material-based nonlinear optical mirror. So all you have to do is we have to image this sample onto this 2D material flake. So this is the image without any target. Once you keep the sample in the path, you can see the image of the sample being imprinted onto the 2D material-based mirror. So here the sample is imaged onto the 2D material. So how it is done is we make use of a 4F lenses to image this onto the intermediate plane, which is further imaged onto the EMCCD, to the sample, which is further imaged onto the EMCCD camera. Another method is the Fourier plane imaging. So this was the second method which I mentioned in the previous slide. So again, we have the two sources. One is 1550 nanometer source and 1040 nanometer source. And the object is again kept in the IR path. And now the sample is imaged onto the back focal plane of the objective. So that is a Fourier plane actually. So not the sample plane. So you can see that this actually shows the Fourier plane of the back focal plane of the objective. And now when you put the sample here, you can see the image being done in the Fourier plane of the image system. And this is now imaged onto the EMCCD camera, and which is again detected in visible ranging. So we also tried to characterize the upconversion imaging system in both the implementations, that is to understand the image quality or contrast. So we were able to get a very good contrast in the image, and the maximum the minimum resolution was actually limited by the EMCCD pixel size, which was like close to 30 micron is the limit which we got in both the case, both the implementation, rear plane and Fourier plane. And you can see the good contrast for different pitch sizes. So these are some of the representative images shown for both implementation. In rear plane imaging, which shows the 250 micron and the 60 micron, you can see the small gratings. These are the optical images of grating that is actually placed in the path, that is in the objective plane, which I showed before. Yeah, so these are some of the comparison of both the upconversion imaging system, both implementation. So we will also do some additional operation like Fourier plane operation on using this 2D material based on optical mirror. So you can see an upconverted image. So this is actually so the previous image shown was a blocking sample. Now we have a sample that actually transmit the light. So this is the upconverted image without any filtering. So then we try to do high pass filtering, Fourier domain operation, that is high pass filtering and low pass filtering using the same system. So how we did that is like in case of high pass filtering, we actually cut down the low frequency component, and in this case, this low pass like high pass filtering or cutting down of low frequency component was done by using an aperture in the path, which actually cut down the low frequency component. So this image shows the representation of that, and you can see that as we cut down the low frequency components, you can actually see the enhanced edges or like the enhancement of like a high frequency component in the image. And this shows the Fourier spectrum with low high pass filtering. And in case of low pass filtering, what we does is we cut down the high frequency component by making use of a small flake, that instead of a larger flake area, we use a small flake so that it cut down the high frequency component, thereby resulting in a much smoothened image of the same image. So we were not only able to demonstrate upconversion imaging, we could also do some real-time Fourier operation on the upconverted image using this system. So we actually compared the performance of our upconversion imaging system with some of the previous implementation based on nonlinear crystal and metasurface. So we were able to get a different implementation using nonlinear crystals were done with using 50 crystal, long crystals, and the pump power was much higher in this side, but the conversion efficiency was also high. But when we compare the pump power normalized conversion efficiency and across the length, the conversion efficiency which we obtained was almost similar. And we also tried comparing with the metasurface. So gallium arsenide metasurface, which I showed previously, have similarly used some frequency generation, which is similar to what we have done. And we could able to achieve much better conversion efficiency at much lower pump and signal powers. So in summary, we have actually designed a novel 2D material-based nonlinear optical mirror for efficient upconversion. And we made use of particle swarm optimization algorithm in order to optimize the thickness of gassy to get maximum messenger generation. And we also validated the simulation and experimental result. Validated simulation with experiments, and we were able to get a good agreement with that um, nonlinear optical mirror. And the conversion efficiency was at least 2 orders of magnitude higher than that of previous implementations. Mentioned, these are much compact and can be easily fabricated when compared to another meta surfaces. And we have also demonstrated in the upconversion imaging in both the real plane and Fourier plane implementation. And we have also characterized the system by studying the contrast matrices. And finally, the utility of the nonlinear optical mirror for Fourier domain process in real time was also demonstrated in this study. So the more details of this work can be, if you're interested, can be seen in this particular paper, which got recently published in Laser and Photonics Review. And so this was the whole team behind this work. My professor, Dr. Varun Raghunathan, he is an associate professor in Department of ECIAC. And my colleagues, Halal Krishna and Ashish, did the fabrication. And Urmila and Rabindra did the flake transfer and another flake characterization. And we belong to Applied Photonics and Microscopy Laboratory. And the website link can be is shown here. So thank you team Creative for giving me this opportunity. If you have any questions, I can answer. Divya, are you here?
Thank you, ma'am. Divya, you can carry on.
Are there any questions from audience? I'll be happy to answer.
Yeah, Josna, it was really fantastic presentation and good, something new knowledge which student as well as the researcher should know in this domain. Just an explanation how this particular field can change medical imaging in terms of detecting any kind of like there are so many diagnostic methods are there. Can this be a potential tool for any type of a disease diagnostic in near future or something? That is one thing. Second thing is there are certain IR imaging techniques which are already used in videography or whatever photography we see. How does it change in that field also? Two questions. Thank you for giving me opportunity to ask questions.
So medical imaging, so most of the medical imaging, medical diagnostics, like so in case of imaging, right? So we make use of like long wavelength signals, right? For example, as I mentioned in the mid-air wavelength, or so they don't have enough detectors in mid-air wavelength. So you can use this technique to upconvert the mid-air signals to this particular visible range. So again, you can make use of an efficient visible detector. So this actually allows you to image do single point imaging. So you can do a fast imaging, single point imaging using the subconversion image. So I don't know like previously how they use this infrared detectors to image biological samples other than the nonlinear optical process which we use. So actually this we can upconvert any particular long wavelength which doesn't have efficient detectors and use efficient detectors which are available in shorter wavelength range to image the samples. So there are reports on using, I have actually seen reports on using this biological samples in the path and imaging. So there are previous demonstration on that as well. So you can actually get to know the composition of the medical sample that is being and use it for like medical diagnostics. For example, you can study the change in absorption of the IR radiation or mid-IR radiation, which is kept in the path by detecting using this another visible detectors. So that is first question. The second question, what was that, sir? Like,
That's like some IR videographies are there, no? IR photography, videography, where we popularly see in many animal what you call detections.
Okay.
In that field, how it can be used, these particular techniques?
So the technique, can be applied in any field, irrespective of the field. So you can actually use this mirror to convert whatever IR frequency. For example, so we have actually enough advanced material like photo detectors available in IR and SCMOS cameras, which are much used in, and this can be actually integrated very easily to any existing systems like portable device like mobile phones, camera. So you can actually kind of fabricate this device very easily into the existing system. So yeah, this can be used. Yeah. So it has its own advantage compared to the other systems. Yeah.
Thank you. Thank you so much. Maybe a last comment I would like to
Yes.
make you is James Webb is collecting a lot of IR data. If
Okay.
you no, when such data is only given to you, like their images, since you are also, if my understanding is correct, there was an upconversion of IR to optical, correct, right?
Yeah, so IR is converted to visible wavelength. Yeah, IR
Visible.
image is converted. Yeah, so IR actually the photon is converted to a visible photon,
Visible, yeah.
which is being
No,
detected. Yeah.
no, what I'm trying to just, maybe my correlation may be wrong, but still, IR images of James Webb, which is coming out now, many,
Okay. Yeah.
can those be converted into visible with your techniques, whether anybody has done? I mean,
So
just.
so actually the already existing image, right,
Yeah.
cannot be converted to visible. So you can use this technique in the path while acquiring to get the image in the visible region. That is how.
During the generation of IR image itself, you should apply this technique and convert
Yes,
that
yes.
into visible.
Yeah,
But if you
yeah,
have
yes, yes,
already,
yes.
you cannot convert that into visible, correct?
Yes, yes.
If you have already, okay, got it. Thank you so much. All the very best.
Good afternoon.
Good afternoon, sir.
Am I audible?
Yes, yes, sir. I can hear you.
Yeah, my question is very layman question. Just I'll
Yeah,
ask
sure.
myself. I am Sanjeev Gaur from ISRO.
Okay.
I had two reasons for attending this webinar. One is I started my career in ISC, that too in ECE department, way back in 86.
Oh, nice to know.
Professor Satyam was, Professor Swande was the director of that ECE, that ECE chairman of that one. And it was very nice to see such a tremendous work is being done in ISC in ECE department. And recently also I visited ECE. Sorry, I'll take some 2-3 minutes with the permission.
Yeah, fine. Totally fine.
Yeah. So I visited ECE. It was a proud moment to visit. Last year I visited just as a son. So that time we were doing that MOS capacitor, MOS. It was the state of the art that time. MOS capacitor, MOS FET side, even silicon dioxide, SiO2, growing O2 on the Si. These things we used to do. Professor Satyam, NN Biswas. These are the people. Even today, after 4 decades, I am feeling proud about working with these people actually. So that is one reason. Second one is that I wanted to know, because this is a very new subject for me. I'm basically a satellite communication person. Now I'm looking after this SRQZ group here, system reliability. Second reason is I wanted to know what is the scope of one of our colleagues. I think I don't remember previous who has asked the question. He asked that one. How you can enhance the IR signal which you receive from the satellite which takes the IR images, so that whether it is scope for improving the resolution of the images. In that direction, if you can throw a light, it will be useful. Anyway, I'll compliment all the team, including Dr. Jyotsna, very nicely. Even though it is a very new subject for me, I got so much interest and I got to motivated to ask some questions also here. And
thank you, sir. It's a privilege to hear.
Nice. And I am also take this opportunity to congratulate Srinath, Giridhar, and Divya, all other team of Creactive, which is doing wonderful job in the field of technical webinars for students, academicians, and researchers. Wide range of audience is benefiting from this one. Okay, madam, you can please announce whether we can improve the resolution of our images by using this technique.
Thank you so much for asking this question. Actually, yes, we can improve the resolution. So how it actually works is like since we are up converting, right, the 1550 nanometer to a shorter wavelength. So the automatically the resolution, right, the resolution of the image is being improved. How is it actually happening is like in the diffraction limited resolution, right, of a 1550 nanometer beam was like will be at a large at much larger than that compared to at 622 nanometer. So you will the diffraction limited resolution at 622 nanometer will be much higher than compared to 1550 nanometer. So this all happens in that ISFG conversion process. So you will get an improved resolution image compared to the one which you take with 1550 nanometer beam. So that is a case which I have demonstrated. That is why I am particularly mentioning the wavelength. So since we are up converting the frequency or down converting, like whatever the wavelength is being like cut down, like 1515 to 622. So the diffraction limited resolution itself is being improved in this up conversion process. So definitely the up converted image will have a better resolution compared to a direct detection of 15. So yeah.
Yeah, thank you very much. Thank you for the opportunity to participate in this one and ask the question. Thank you.
Ma'am, I want to know what's your advice for photonic students?
Photonic students advice. So, so all you have to do is like you have to be hardworking, and you have to be very dedicated to whatever you're doing. The rest will come as such, is what I understood from my PhD journey. So I was actually I joined in for my PhD in 2019, and NIAC I joined as an research associate actually under Varun Raghunathan, and I didn't have the courage to apply for PhD until I cleared the written maths test. I was like worried whether, since being from non-IIT, I was worried whether I'll be able to and get an opportunity to do work at IAC. But that actually tried me to work harder and clear the maths test for that particular interview, which actually led to my PhD. And so all you have to do is stay focused, and you do your work in whatever way, be dedicated, be hardworking, and focus on the recent work, what is happening in the photonics domain. And if you have a good group of people, which I was blessed with actually, my professor and my colleagues were the best, I would say. So with all their efforts, and finally I got my PhD, and I feel really proud to be presenting in front of all these prestigious people. So thank you, team, for this opportunity. So it was a great honor for me to present here, my work here. Yeah.
Now, just to add, Jyotsna, what she has told, I mean, those who are really passionate about physics, definitely you will achieve greater heights, which Jyotsna is one of the students of Professor Varun. He is also joined here. Please make sure that your fundamentals are very strong and you focus on your study and look for research opportunities. Of course, there will be difficulty. It is not a easy cake walk or anything. Definitely difficulties are there. Once you come out of difficulties, bright future is there in research, both in terms of science and technology, not necessarily, but physics is a fundamental thing. That's what we trying to, what you call, communicate or propagate in our forum through weekend talks, and even trying to bring students to IAC, RRI, Indian Institute of Astrophysics. Many areas are there. Only thing is, students should not be behind money. They should be behind knowledge and pure research. Definitely it is going to give a good future. Definitely difficulties are there. It is not easy. You have to start your life with difficulty. Thank you, Josna, for allowing me. Professor Varun is there. Professor Varun is there. If you wish to have any comment or suggestion or for students, we will be happy to listen to him.
Good afternoon, sir. I hope you're able to hear me. Yeah, yeah. So, yeah, I just wanted to attend Jyotsna's talk just to hear what she had to say. That's all. But just to reiterate what Jyotsna was saying, I think hard work really pays off, right? And then it always helps to like always make sure that every 6 months or a year try try to ask the question, why are you are doing what you are doing, right? And then make sure you really enjoy what you are doing. Also, you should be passionate. It should not be forced that you are doing something which you don't like and all that. So then only you will be able to be highly productive and then do very good work. And then find the areas where you would really like to work on. And then they say there's this famous thing, right? When you do something you like, right, then time just flies, right? You don't even keep track of time at that point. So if you have to find something like that and do very good work, and I'm sure all the students would be very successful, right? Yeah, that's all I had to say. Thank you.
Thank you, Professor, for such a beautiful words. It's inspiring to many students. Thank you so much.
Thank you, sir. Thank you, ma'am.
Thank you.
Just poll Divya if anybody has to say anything, because another 4-5 minutes is there. If not, maybe you can conclude, Divya. Just
Okay,
check.
sir.
I think it was a good talk, Josna. It is recorded. It is available in our YouTube. Many people, many students can refer later. Thank you so much for your time and a really very illustrating talk. Thank you so much.
Thank you, sir.
Divya, you can conclude, ma.
Okay, ma'am. Thank you, ma'am, for your good speech.
Okay. Thank you very much, ma'am, for engaging us with your wonderful, informative talk. And we are very thankful for Arya sirs for recommending you. And we are thankful for all the participants for